The sun is far from static. It's a very dynamic, very variable object. And a significant key to that variability is magnetism. So in this segment, let's consider the active sun and the magnetic effects and how they influence what the sun is doing. Sun can be considered a ball of swirling gas, actually plasma, charged gas, charged particles, and that causes it to have a tremendous amount of magnetism, kind of like a big bar magnet, although the sun is much more complicated than a simple bar magnet, which is actually a pretty good representation of the magnetic field of Earth. The sun has differential rotation, and because of the faster rate of rotation on the equatorial regions than in the polar regions, that makes the picture a lot more complicated and produces all the magnetic phenomena that we're going to discuss, and that has significant influence in terms of what the sun is doing and influence on its effects on Earth as well. As mentioned, the magnetic field of the sun is quite chaotic. It would be relatively simple if the sun rotated at a constant rate across all parts of its surface, but we have differential rotation. Because of differential rotation, we have a twisting effect. The faster moving plasma dragging the magnetic field along the equatorial region, distorting it like you see there, and distorting it even greater amounts as the months go by, to the point where after 11 years, the twisting and distortion is so severe that there are forces inside the sun that cause it to reset and start all over again. But when it does that, after 11 years, it resets itself with an opposite magnetic polarity that it started with. So an 11-year cycle, at the end of it, it resets itself oppositely polarized. The magnetic field is oppositely polarized. And that can actually be observed in the phenomena of the magnetic loops that exist on the surface of the sun, which turn out to be sunspot pairs, and such that in the northern hemisphere of the sun, as it's rotating like this, in the northern part, the loops that are formed magnetically are preceded by a north pole, which goes into the surface of the sun, and a south is lagging behind, coming onto the surface of the sun. In the southern region, the southern hemisphere, the opposite is true, such that the leading polarity of the loop is a south pole coming out, and lagging behind that is a north pole going in. After 11 years, this all reverses, and these magnetic orientations are reversed as well. So that's the basic scheme for looking at the big picture, how the sun's magnetic orientation reverses, and an overview of why it does that. Magnetic fields always exist in loops. And so as these magnetic fields are looping inside the sun, we just saw that when they really get twisted up, sometimes they emerge from the sun. But when they do, they go back in and continue their loop inside the sun. Well, that magnetic field coming in and out is associated with the sunspots, these darker regions against the surface of the photosphere. So strongly related to a magnetic field activity in the photosphere. They look dark, not to be fooled. They are not black. It looks black here in this image simply because compared to the temperature of the regular photosphere at 5800 Kelvin, these sunspots are around 4500 Kelvin. And because of the relationship of temperature and luminosity, with greater temperature, the luminosity goes up rapidly. And so in comparison to the 5800 Kelvin, the 4500 Kelvin looks black here, looks dark. But it turns out that it would actually shine very bright. That sunspot by itself would outshine the full moon if it was just sitting there all by itself. So it's basically red-orange in its color. And the center region is known as the umbra, and the penumbra, the region outside, not to be confused with umbra and penumbra regions of eclipses, but the idea is similar or analogous to some extent. And these sunspots are pretty big. They can actually engulf the entire Earth, so they are not small little regions. Now, we know that the sunspots are magnetic in their origination because something known as the Zeeman effect that can be tested in the lab is when you have iron absorption lines, not in a magnetic field. That's what's shown here. And then the region in the sunspot itself, you see a splitting of that iron absorption line into 3 separate lines, and that's the signature of intense magnetic fields, the intensity of which is related to the degree to which those lines are separated. So that's the Zeeman effect. So this is certainly a magnetic phenomena, these sunspots. A little more detail on the sunspot pairs. We have these pairs connected by tightly wound magnetic field lines that have trapped the gas. So that's one of the things the magnetic field does, is traps the gas. You can actually see it. Therefore, you can see the magnetic field line geometry. And in addition to that, as we mentioned, the photosphere is about 5800 Kelvin. The spots are cooler. Magnetic energy is partly responsible for the cooler regions. But even more so, magnetic fields put forces on charged particles, and that's what the plasma is. So in this region of strong magnetic field lines, the magnetic fields prevent the hotter plasma from entering into this region of cooler plasma. And so it prevents an equalization of the temperatures, and we're down to about 4500 Kelvin in that region. So that is the basic physics of what that's doing. And here is a visual picture of the magnetic loops that are manifested by the light emitted from the electron transitions in the ionized gas, producing photons. We can see the geometry of the magnetic fields themselves. I couldn't resist this image of a single sunspot. It looks so ominous, like some alien creature. It looks like if you stuck your fist in there, you'd come out with a bloody stump. But of course, that's the wrong perspective. As I mentioned, some of these sunspots are the size of Earth. They would engulf the Earth, so this particular alien monster could eat the whole Earth. And in this little video sequence, we can see how the sunspot pairs are morphing. They're evolving as they go around. You can see that if you watch how they change. So over the course of weeks, they can exist, but they change quite a bit. So just to review the solar cycle, we've already mentioned the 11-year cycles, and we can see that here. Based on the number of sunspots, the sunspot activity varies over a period of just about 11 years, where we have sunspot maximum and minima. So that follows an 11-year cycle, and at the end of each cycle, we have a reversal of the magnetic polarity. So that's where the leading and trailing edges of the sunspot polarity reverses. So the particular polarity of the sun's magnetic field can be seen in that way. So we have a total solar cycle equal to 22 years, at which time it starts all over again with not only the renewal of the sunspot activity sequence, but also the same magnetic polarity orientation. A couple of interesting phenomena associated with the sunspots. We have what's called the Maunder butterfly diagram, which is really a diagram showing each of the 11-year cycles. Each of these butterflies are in another 11-year cycle, and it shows the relative sunspot activity and its position on the sun. So here's the equator, and here are different latitudes, 30, 90. All right, so we can see that at the beginning of the sequence, the sunspots are actually at greater latitudes, and then as the cycle progresses, the sunspots migrate toward the center, so they're concentrated more toward the equatorial regions, producing this butterfly-like diagram. Not well understood why it produces this particular sequence of sunspots, but that's what it is. And then there was an interesting phenomena back a long time ago, from 1645 to 1715. As we look at the historical records, again, now this is a compressed graph. Each one of these spikes is an 11-year cycle. But during that period of time, there was very, very little solar activity. So the sunspot activity was exceptionally low. And at the same time, there was exceptionally severe winters in Europe. So this blue plot overlaid on this shows the severity of the winters in Europe and London and Paris. And nobody knows for sure, but there's this interesting potential correlation here between the sunspot activity and the severity of the winters. This was even called the Little Ice Age because of how cold it was during those years. Interesting thing to think about. Nobody knows for sure. Some more solar magnetic effects and terminology. We see here sunspots, so we're familiar with those now. Over here, there are some hot spots, which seem to be associated with sunspots, but they precede sunspots, regions where the solar surface brightens, called plas. And that's kind of interesting. It seems to be associated with the magnetic field energy coming toward the surface of the photosphere, producing increased energy at those regions till the magnetic field bursts forth out of the photosphere. Well, magnetic field lines can loop high above the surface of the sun and trap the gas within, as we've mentioned, and that trapped gas makes giant solar prominences. So there's a really huge solar prominence. Here's a solar prominence on the surface. So there's a wide range of possibilities of sizes of these prominences. Huge regions of trapped gas. At times, Jupiter could fit within the loop, which is pretty incredible. Turns out that we also have a structure called filaments, but that seems to be appropriate for what you see here. But what these filaments really are is a prominence from a different geometry. Namely, looking from above, they look like these filaments. If you look at them from the side, turns out they are the same thing as prominences. And now let's consider some of the most violent solar phenomena. We've discussed solar prominences already. Well, yes, it traps the gas in magnetic field loops, but not always, because sometimes that plasma is so energetic the magnetic loops cannot contain it, and the plasma breaks free and lifts off billions of tons of charged particles, blasting off from the surface of the sun. This is known as an eruptive prominence. So that's a pretty potentially severe magnetic phenomena. Then in the background of this slide we see the sun, and what is this? What phenomena is this here? Well, that's called a flare. In fact, that's a very large flare. And a flare is a violent magnetic phenomena that starts on the surface. It's kind of like a plasma particle eruption that can be produced by things like sunspots colliding with each other that initiate this process. And literally, the amount of energy associated with a flare is comparable to the entire energy of all the fossil fuels buried in the crust of the earth. And these flares can happen at a rate of as much as 1,100 flares per year at the peak of the solar cycle. So the energy associated with those flares, as I mentioned, is really huge, and it can actually cause the sun to vibrate for hours after a flare blasts off its high-speed particles into space. The most violent and energetic events of all are known as coronal mass ejections, where you have literally trillions of tons of particles blasting off from the sun. So these are the events that are associated with geomagnetic storms on Earth if they happen to be oriented toward us. So we hope that's not too often the case. It literally produces so many charged particles that it overwhelms the protective shield, the Van Allen belts of the Earth, and the charged particles bust through that and can wreak havoc on satellites and the power grids on Earth, and this can have serious potential implications. One of the more visually pleasing aspects of a CME is the aurora borealis, or in the case of the southern hemisphere, the aurora australis, which is associated with these charged particles breaking through into the atmosphere, interacting with the oxygen and nitrogen atoms and causing electron transitions, producing wonderful light displays as the photons are released from the electron transitions. But right now, let's sit back and observe some recent footage at high resolution taken of solar phenomena that give you a visual experience of some of the things we've been talking about. Keep in mind that all the phenomena observed here are rapidly sped up in time. Huge solar prominence. Look at the high resolution prominences we see here. There's a flare, huge flare blasting off the surface. Different wavelengths are being highlighted in different scenes here. Sunspots morphing, evolving over many days here. Looks like an ultraviolet sequence. See the rotation of the sun. Several days here. The collapse of a huge prominence, it appears. Super high resolution sunspot.